Okay, thank you for joining us today. Welcome to this technical walkthrough for Volks Finance. We're pleased to have Gidon from Volks Finance with us and the rest of their team. We'll be demonstrating the main functionalities of their code base and providing valuable insight about their protocol. From Immunefi side, I'm Daniel, and with me is Artem, our technical expert. Volks Finance Boost is already live with a 100K reward pool waiting for you. You can check it out on our website at immunefi.com/explore/boost. Without further ado, Gidon, the floor is yours.
Yeah, hi. Can you hear me? All right.
Yes.
Okay, thank you for having me. Yeah, I'm excited to share with you the technical walkthrough of the new product we have at Volks Finance. So a bit about Volks Finance. We are a DeFi protocol that was built on Algorand, and we have many products on Algorand. But this new product that we're offering is a cross-chain lending protocol that is EVM based. So through this call, I'll just introduce you to the protocol, give a high-level overview of the docs, and then I'll end by diving into the code and talk about some of the key areas. Can I share my screen? I'm not sure if that's possible. I don't have permissions, doesn't look like.
I think I already made you a contributor, so it must work. Maybe actually updating the page in your browser will also fix this.
Okay, I'll refresh the page then.
Let's wait for Gidon to return on this call. A couple of minutes.
Hey, welcome back.
Now it seems to work.
Great.
Cool.
Okay, I'm sharing my screen. Can you see this?
Yes.
Okay, so if you look at our Immunefi Boost page, we link to a number of docs, and you can find them, all the links on that page. The one I would recommend you look at to begin with is the cross-chain lending protocol design. So the first thing I want to talk about is why do we decide to build a cross-chain lending protocol? And there's two important aspects. One important aspect is that users want to, when they select a protocol, they choose for convenience. So they want to use their favorite blockchain and the wallets they're most familiar with. So having a cross-chain protocol lowers the barrier to entry for these users to join your protocol, because you're more likely to have the chain and wallets that they support, that they like supported. The other important aspect is liquidity. By aggregating all the liquidity from various chains, you collectively have a lot more liquidity in the protocol, where if you compare that to, let's say, deploying the protocol across multiple blockchains, but all separate, distinct from one another, having a multi-chain, cross-chain protocol allows you to unify all the liquidity, which is much more efficient. So the way we do a cross-chain lending protocol is we have the hub and spoke architecture. So the hub chain, which is Avalanche in our case, that stores all the logic and the state of the protocol. And the spoke chains, which all connect to the hub chain, those are what their user interacts with. So a user would submit a transaction to the spoke chain, and then there's some sort of communication between the spoke chain and the hub chain, and then some state is updated in the hub chain, and maybe liquidity is also stored there. The way we do the communication between the spoke chain and the hub chain is by using wormhole messaging or Chainlink CCIP, and both of these are messaging protocols. In addition, we also integrate with Circle CCTP to support USDC transfers from the spoke and hub chain. One, I guess, important aspect is that when you think about a cross-chain protocol, or just like cross-chain applications in general, one example that may come to mind is bridges, where you're transferring a token from one chain to another. And I guess if any of you have used bridges, you'll be familiar that you don't receive the token immediately on the destination chain. You have to wait for finality on the source chain before you'll get the token on the destination chain. And this is to prevent double spend attacks, where the original source chain where you locked up the liquidity, that block gets dropped, and you actually get back the token you originally sent, but you still receive the minted token on the destination chain. So we similarly have to care about finality in our protocol, even if we're not necessarily bridging tokens. So an example could be that if a user is locking up, let's say, collateral on the spoke chain, and we're just relaying a message from the spoke chain to the hub chain saying that this user has locked up, I don't know, 1 ETH, we can't do anything with that until we know for sure that ETH that they've locked up on that spoke chain is for sure locked up. So waiting for finality not only applies to bridging tokens, but more broadly applies to what we call value transfers. So value transfers is either if you're bridging a token, or you're just saying that I've locked up some token and credit me on this destination chain. When it comes to the liquidity of the protocol and where the tokens lie, we take a hybrid approach, where for some tokens, the liquidity remains on the spoke chain, and for other tokens, the liquidity is bridged over to the hub chain. So for tokens that are native to a particular blockchain, for example, Ether on Ethereum, that would remain on the spoke chain. But for cross-chain tokens like USDC, those are all bridged to the hub chain. So we've covered the design, broad overview of the design of the hub and spoke and messaging and so on, but I want to dive a bit deeper into the cross-chain messaging architecture. So I mentioned that we leverage wormhole messaging and Chainlink CCIP messaging. So how do we actually use these messaging protocols? So the way it works is that for a contract to be able to send and receive messages, all it needs to do is inherit from this bridge messenger abstract class smart contract that we define. And if it inherits from this contract, then it gains the ability to send and receive messages. And because we integrate with multiple different messaging protocols, we want to abstract away the differences between them, because Chainlink, CCIP, and Wormhole have different interfaces when it comes to sending and receiving messages. But from the person who's sending the message and receiving the message, they don't care about who did the sending or receiving, whether it's Wormhole or CCIP. All they care about is the actual message itself. So to abstract away the difference, we have this smart contract called the bridge router. And its responsibility is to take a message and direct it to the messaging protocol that you decided to use. So the bridge router would forward the message to a bridge adapter. And a bridge, for every single messaging protocol we integrate, it has its own bridge adapter. So you can imagine a bridge adapter for Chainlink CCIP and a bridge adapter for Wormhole. And each particular adapter would take this common interface that we defined that abstracts away the differences, and then convert it to the format that Wormhole or CCIP expects. So that's what sending messages work. That's how sending messages work. When it comes to receiving messages, it works the opposite way, where the message would first be received by the adapter, and then it would forward it, or then the adapter would convert it to a common format that the bridge router expects, and it forwards the message to the bridge router. And lastly, the bridge router would then pass on the message to the bridge messenger, who will be responsible for handling the message received. Just to touch on the other two documents that we provided, we also have the lending formula. So this lists out all the formulas we use in the protocol and a bit of explanation about how each one of them work. So you can check that out in your own time. And lastly, we have this operation lifecycle document. And this goes over the lifecycle of an operation from the time that you initiate it on the spoke chain to it being finally handled on the hub chain. And you can see it can get quite complex. So I'd also recommend that you read through this. I'm going to now start sharing the codes so we can start diving into that. So you can find the link to our code base in the Boots program. If you clone the repo, then all you have to do to set up is just run these two commands, npm install forge install. So rather simple. And then to build is npm run build. The code base is split into 4 folders. The 4 folders are the bridge folder, which contains all the contracts relating to sending and receiving messages between the spoke and hub chain. These contracts are deployed both on the spoke chains and the hub chain because you need to both send and receive messages. And for some operations as well, messages are being sent from the spoke to the hub and some from the hub to the spoke. We also have the hub folder. So these contain all the smart contracts relating to the core business logic of the protocol. So this is like the actual main lending protocol. So you'll find all the contracts about like how to handle deposits, how much a user can borrow, liquidations, and so on. We have contracts Oracle folder, which contains all the contracts relating to the Oracle prices. And since all the core business logic of the protocol is on the hub chain, we actually only need the Oracle prices on the hub chain. So the Oracle contracts are only deployed on the hub. Then lastly, we have the spoke folder, which, like I've mentioned, is the contracts that the user interacts with most of the time, where they would call the spoke contract, and then messages are relayed with the bridge contracts to the hub to be handled. So I think it'll be useful to go over a practical example of how an operation would work. So we'll talk about one of these operations, create account, which is the first operation a user must do before they can start using the protocol. They need to have an account. So you may be wondering what an account is. So if you use a normal protocol on just a single chain, then the way you identify a user is just by their address. However, in a cross-chain environment, an address alone may not be sufficient in and of itself to identify a user. Therefore, we have a concept of an account where each user has their own account. An account contains a list of chain address pairs. So like I could have my own account and I could have one address registered to that account on Ethereum, and then another address on Avalanche, and maybe another address on a non-EVM chain, which has a completely different format. And the account is meant to abstract away the differences between the different chains and how they define addresses, as well as give the ability for users to control their positions no matter what chain they're on. So this is what an account is. And you'll see from the type, it looks just like that. So we have an identifier for an account, which is just a bytes 32. And then we have basically a mapping of the various chains that you have registered and the address. So if we move back to the spoke common, which is the contract that the user would call. So they would call the create account method here. And what it does is that spoke common inherits from the bridge messenger abstract class. And this was the class I mentioned earlier, which allows you to send and receive messages. So by inheriting from this contract, this spoke common can send a message to the hub. So this is basically what the operation does. So it calls the internal function do operation, and it passes in, if I go back to it, it passes in the parameters relating to how you want to relay the message and the action the user's taken. In this case, since it's the create account method, we're passing in the create account action, and then the account ID that they're creating, and also any parameters relating to the operation. So it constructs the message, and it just sends the message using the bridge messenger interface. So a bit about how this message is defined. So a message to send contains the following information. The first is the params, which is the metadata relating to how the message is sent. So the first one here is adapter ID, which is basically how you want the message to be sent. So this would like reference wormhole or CCIP. We have return adapter ID, where in some operations that require a message to be sent back from the hub to the spoke, how do you want that to be done, through which messaging protocol. We have receiver value, which is that if you want to receive some gas token on the destination chain, you can do so by paying a higher fee to do the operation on the spoke chain, and you're credited with a bit of gas on the destination chain. You have gas limit, which is how much gas limit to use when you receive the message on the hub chain or on the destination chain. We have return gas limit, which is if there's a return message, how much gas do you need for that transaction. So those are the metadata relating to messages. We also have other variables here, such as the sender. So if we go here, the sender in this case is spoke common itself. And this is a very important thing that the receiver of the message needs to verify, because anyone could fabricate a message and send it to a contract. And it's important that the receiver of the message needs to verify and say, okay, this message comes from a trusted source. So we have this sender. We have the chain that we're sending the message to. In this case, since we're on the spoke and we're trying to create an account, we have to send the message to the hub chain. Where should this message be handled? So, okay, we know that we're sending it to the hub chain, but who should actually receive the message and handle the message? And lastly, we have the content payload of the message. So the action was create accounts, the account ID, the person who's actually sending the message, the user address. And then we have the finality here, where since this transaction involves no value transfer and we don't care about finality, we can do immediate finality. And we call the send message internal function here, which is from the bridge messenger, and it then forwards the message to the bridge router. So like I mentioned, the bridge router abstracts away all the differences between the messaging protocols. So if we look at the bridge router, and we just called send message, so it would check the adapter that you're trying to send the message through, so wormhole or CCIP. And then based off of that, it would do some other like sanity checks, making sure that the sender is really the sender, because that was a defined variable inside message to send. Checking like, do you have enough balance to pay for the message fee? And then we lastly direct the message to the particular adapter. So if you actually look at the adapters, we have 4 different types of adapters. So we can split them into Wormhole and CCIP, the 2 messaging protocols we use. But then we also have 2 variations of each, where we have Wormhole Data Adapter, which just sends data and no tokens. And then we have Wormhole CCTP Adapter, which sends a Wormhole message along with a USDC transfer. Similarly, we have CCIP Data Adapter, which sends data messages through CCIP. And we have CCIP Token Adapter, which couples a CCIP message with a token transfer. In this case, since we're doing the create account operation and there's no token being transferred, the user would specify either to use the Wormhole Data Adapter or the CCIP Data Adapter. One other adapter that I didn't mention is the hub adapter. So the hub adapter is that you can imagine that if you remember the diagram I showed earlier where we had the hub and spoke architecture, where we had all these spoke chains that were connecting to the inner hub chain, and the hub chain was Avalanche. So what happens if a user wanted to do an operation on Avalanche itself? So there's 2 ways you could have deal with this problem. One way is that you just expose a function on the hub chain to directly do the operation. Or alternatively, you could register the hub chain as well as you could register the hub chain to also be a spoke chain. So we chose for that latter approach so that we had this common way of doing operations irregardless of what chain you're on. So now that we have this spoke chain deployed on the hub chain, like what does it mean to send a message at this point? You wouldn't really use Wormhole to send a message from Avalanche to Avalanche. So therefore, we created this hub adapter, which mimics the behavior of a messaging protocol. But what it really does is that it takes a message that you want to send and it immediately receives it on the destination chain. So from the hub's perspective, when it's receiving the message, it doesn't care whether it's come from the hub, it's like a spoke chain deployed on the hub or a spoke chain on a different chain. All it knows is that, oh, I was just sent this message from an adapter and I need to handle it. So that's all about sending messages. So we'll now see about receiving messages. So we'll look at Wormhole Data Adapter as an example. So we sent a message using the Wormhole relayer, and the Wormhole relayer will then call this receive Wormhole messages function with the way that Wormhole defines messages. So since we don't want to implement the same function multiple times for each adapter, what we do is we convert the message we received in the formats that Wormhole provided. In this case, it just provides as a bytes payload, and we convert it into the format that we expect, which uses the struct message received. So message received contains a message ID, which is the unique identifier for the message. And we combine that with the adapter ID to say that to uniquely identify a message. We have the source chain. So this is where the chain, this is where the message is sent from. We have the source address. So this is where the message was, which actual smart contract sent the message. We have the handler. So that once we receive the message in the adapter, who should actually end up receiving and handling the message. We have the payload, so the contents of the message. And lastly, we have some metadata relating to that if there's a message to send back, how should we do that? Which messaging protocol do we use, and how much gas limit will I need to send the message back? So once we've converted to this message received struct, we call the bridge router receive message. And what we do is we check to see first, like, are we getting this message from a known adapter? If so, then we proceed. Then we check to see whether the message has already been seen, because one I guess, possible attack would be that someone could replay the same message. That, let's say you deposit 1 ETH once, and then you receive the message on the hub twice. In that case, you would be credited with your account with 2 ETH when you only really deposited 1 ETH. So this check should prevent that from happening. Lastly, what we do is we try to receive the message on the handler, and we use a try-catch block to do the receiving of the message, because we want to prevent a scenario where we revert when we receive the message. Because if we end up reverting when we receive the message, it could be that the user loses access to some of their funds. So if we take the deposit example again, if a user tried to deposit 1 ETH and a message is relayed from the spoke to the hub, and we try to receive the message in the hub, but for some reason it reverts, then the user is not only not credited in their accounts with the 1 ETH, but they have no way of recovering that deposit that they made. So they lost their 1 ETH and they got nothing for it. So the idea behind this try-catch block is to ensure that if it does revert, then we catch the error and we have mechanisms in place so that the user can recover from that scenario. So the bridge router also has 2 additional functions, which is retry message. So in that case, it would check, has the message failed before? If it has, then try to receive it again. And if it's successful, then we can proceed as if you received it, it went through the first time. Otherwise, we put it back in the failed messages mapping. We also have reverse message, which can also be named cancel message. This allows you to cancel an operation. So if we had the deposit 1 ETH example, if you were to cancel this message, then what would happen is that if you look into the implementation of this, then it would send a message back to the spoke chain saying that your deposit never went through, send back the original funds to the user. And that is implemented through this reverse message mechanism. So we saw how the bridge router receives messages and handles errors. So what about the actual handling of the message itself in the bridge message handler? So going back to the example of a create account, we sent a message from the spoke. We received it on the adapter. It was forwarded to the bridge router. And now we actually need to do something with the contents of that message. So the contract that receives the message is this hub contract. And if we look at Bridge Messenger, to receive a message, all you need to do is you override this internal function, underscore receive message. So if we look at the implementation for that in the hub, it has a large if-else block. And depending on the action, it directs it to the appropriate channel. So in our case, if it was a create account action, then we would call the account manager and the create account operation. There's also checks like this. I mentioned earlier about how it's important to verify that the message you received is from a known sender, because messages can be fabricated. So we also have the spoke manager to ensure that the message is coming from a sender that we are aware of. I think, so spoke common, we saw an example of create an account, and there's also many other operations within this contract where they all do not require finality. So every single operation, all we care about is the intentionality of the user, and there's no value being transferred. So like a message to withdraw, like you're not actually sending any funds when you want to withdraw. So again, we don't need to wait for finality. For all operations that do require finality, those go through the spoke token contract. And the 3 operations we have are create, loan, and deposit, deposit, and repay. We have Spoke token is an abstract contract, and we have 3 implementations of spoke token, depending on the type of token it is. When we were looking at the docs, I mentioned how we take a hybrid approach when it comes to bridging tokens. For tokens that are native to a specific chain, we don't bridge them, whereas for cross-chain tokens, we do bridge them. So spoke, circle token are examples of tokens we will bridge, whereas the other 2, spoke gas token and spoke ERC20 token, are tokens that are not bridged. When it comes to messaging, we have an additional argument which we skipped over, which is extra args. And extra args are used when you want to send a token or receive a token. Send a token and receive a token when you're actually bridging them from the spoke to the hub. So you can see that spoke circle token makes use of the extra args. Since spoke circle token, all these spoke token contracts, they so like I mentioned before, so spoke token requires finality, whereas spoke common doesn't require finality. When it comes to the adapters used as well, there's a difference. Where with spoke common, since they all only sent messages, they use the wormhole data adapter and they use the CCIP data adapter. Whereas spoke circle token, since it involves a USDC cross-chain native transfer, then it will make use of the other 2 adapters, the CCIP token adapter and the wormhole CCTP adapter. As well as this, when it comes to transferring tokens, if you're interacting with the spoke chain on Avalanche, which is also the hub chain, then you would actually not use these token adapters that I've just mentioned for the same reason as before, because there's no actual message to be relayed. Rather, the hub adapter again supports sending and receiving tokens through mimicking the behavior of a bridge. So we've covered so far all the messaging between the spoke and the hub. And that's one very important aspect of the protocol. But the other important aspect is the actual lending protocol itself, which is almost entirely contained within the hub. So the way we do lending may be slightly different to some other protocols, where we have the concept of a loan type. So a loan type, what it does, it baskets, pools together or tokens together, and allows loans to be taken among those tokens. So if you have used Aave before, when you go on their protocol, you'll see that you only have one position. Whereas with us, in our protocol, you can have multiple positions through creating multiple different loans. And each loan is separate and distinct from one another. And when you create the loan, you have the ability to select what loan type do you want. So one thing that we can offer is we can offer higher loan to value ratios by basketing together price correlated tokens. So you can imagine we have a loan type called stablecoin loan type, and all that would contain in those loan in that loan type would be stablecoins like USDC and USDT. And by limiting the loan to just those tokens, they can offer like 90 or 95% loan to value ratio on those tokens, compared to if you were using like USDC as collateral with Bitcoin as a borrow. In that case, then those 2 tokens are not price correlated with one another. So at that point, the loan to value ratio would be a lot lower. So we have this concept of loan types. So these is all contained within the loan manager contract. So you could create a loan. And when you create a loan, you not only have an identifier for the loan, but then you also specify the loan type that I just mentioned. And since you can have multiple positions, you could, like a single account may have 5, 10, 15 different loans. There's no limit. And each one would be separate from one another. So if you get liquidated in one loan, it doesn't affect any of your positions in any of the other loans. We have as well 2 variations of the pools on the hub chain. We have the hub non-bridge token pool, which like the name suggests, these is for the hub pool or pools on the hub chain where the token is not bridged from the spoke. And then we have hub circle token pool, which is for USDC and other tokens that are bridged to the hub chain. And that's where the liquidity remains on the hub rather than on a spoke, like in hub non-bridge token pool. The difference between these two is that which contracts can interact with the pool. In the case of hub non-bridge token pool, since this refers to a token that lies specifically on one chain, the only contract that can interact with it is on that single chain. Whereas with hub circle token pool, USDC resides on many different chains, so it's possible that you could deposit and interact with its pool through any of the chains that support USDC. So you have the ability to add different chains, spoke chains to this contract. The hub pool itself, it uses a familiar mechanism to what many of you may know from other lending protocols, is that when you deposit a token, you're credited with an F token. This is not an actual token that is minted, but it just represents your share or represents the deposit that you made. And that there's a simple formula to track the interest accrued using the F token. So let's say you deposit 1 USDC, you will receive maybe like 0.9 F USDC. And then when you come to withdraw the 0.9 F USDC, then the rate could have changed and you would get back more than the 1 USDC that you received. So all the interest is tracked using the F tokens. You can find this in, so if we go to Loan Manager and then Deposits, we have some libraries which implements the logic of the lending protocol. And if we go to here, so update pool with deposit, what we do is we convert the amount that you're depositing to the F amount. That is done through this interest index, which tracks the accumulated interest. And the formula for this is quite simple. You can find all these formulas in the mathutils function for the protocol, where what we do is we just multiply the underlying amount by the interest index, and this gets you the F amount. And if you want to convert it back, then you take the F amount and you divide it by the interest index. So the interest index is a monotonically increasing function. So you always receive back more than you originally deposited. The way liquidations work as well is a bit interesting, because in a cross-chain protocol, you can imagine that if a user wanted to liquidate a position, by the time that they send tokens on the spoke chain and the message is relayed, it could be that the price has changed or someone else has liquidated, which makes liquidations prone to failure if they were to be submitted from the spoke chain. So therefore, we also support a number of direct operations. So these are operations which can only be submitted on the hub chain itself. And one of these is the liquidation transaction. So instead of repaying someone's position when you liquidate, what actually happens is that the debt is transferred to you in your into your own loan. So you have to ensure that you have a sufficient collateral in your own loan after the debt has been transferred to you. So this all happens on the hub chain itself with no messaging. So you know immediately whether it's going to pass or fail, or whether it's going to go through or revert. The other two direct operations we have are deposit F token and withdraw F token. So we have the ability to turn on this functionality where you can mint the F token on the hub chain. So originally when you deposit, we're just crediting in your state on the hub chain, saying that this user has 1 F token, but you're not actually getting to mint any of this token itself. So you have the ability to withdraw this F token where it would decrease your state. So if we go to loan manager state and we see user loan collateral, if you were to mint the F token on the hub chain, your balance would go down inside your loan, but you'd actually receive the token in your wallet. And this may have a number of use cases, such as like pairing liquidity on DEXs, where you can earn interest both from lending and from swap fees. And there could be some other areas, but we won't go into that as for now. So once you are able to mint the F token, we also need a way to burn the F token. So that's for the last operation, direct operation we support, which is deposit F token. So this is after you've minted the F token, you could send it back to the loan manager, and what would happen is that your balance would get incremented again. The last thing I want to speak about is the reward mechanism. So when a user does certain operations, they are credited with, like we can say, virtual points. And we track them using this collateral, borrow, and interest paid parameters. So for every token that they pay in interest, their interest gets interest paid variable gets incremented. And we also have collateral where we define reward indexes similar to deposit interest indexes, which track not the interest that you're earning, but the rewards that you're earning. And these are all stored within these parameters. I think that's everything I want to go through. Yeah, I'll stop sharing my screen. I don't know if there's any questions or.
Well, actually, there's no questions in the chat. Let me actually also check the Discord. Yeah, no questions from the public right now in both chats. So maybe we can go over like our Immunefi Q&A stage. So I was just interested in, maybe you can tell us a little bit about what were the most important bugs that you have received in your previous audits that you haven't really expected to see.
Yeah, I think the most important, I guess, common bugs that we encountered before are just logic flaws. So this is where the implementation of the code is correct, as you imagined, but in practice, the logic has some sort of flaw. Mm-hmm. So this is not an actual bug we received, but an example could be like related to the formulas that you've defined. And it may be like the interest paid by borrowers is less than the interest received to the depositors, in which case then there will be a gap in the calculations. So generally just checking the logic of the protocol and seeing if everything is correct.
Well, despite you don't have like a huge code base, especially comparing to some of the ongoing boosts with like 100K lines of code and more, but still, I'm just interested in maybe you feel that some part of your system are like most important and white hats should focus when they will be looking for bugs. Maybe they will focus on some exact areas that you would like to specify.
Yeah, I think one definitely important area is the communication between the chains. So messages going from the spoke and the hub to the spoke, and our integration with the three protocols, Chainlink, CCIP, wormhole messaging, and Circle CCTP. One thing we do as well is that when we combine the two messages together, we need to make sure that when we receive them too, we also receive them together. So making sure the link between the two, a message and the actual transfer of the USDC, that is airtight and there's no way to like mix and match between the two. The other, I guess, important aspect is just the lending protocol logic in general, which you can separate it completely from the cross-chain communication. And you could just view as like a normal lending protocol you would find.
Got it. Thank you. Also, like, yeah, we'll have this call in recording so white hats can rewatch it. But I was also interested in maybe you can share some resources or articles that can help white hats learn more about your project and the code base.
Yeah, so I think the best place to start is the documentation we began with. So you can find a link to that all on the Boost page. And I mean, it's quite a long document, 40 pages or so. So it should go into quite a lot of detail into how the protocol is intended to work. So looking at that, I think could be very helpful. As well as that, we'll be releasing a public testnet quite soon. So if it's confusing how operations go from submitting it on one chain and being relayed and it being handled on a destination chain, it could be useful to white hats just to interact with the public testnet through the front end that we provide. And then just verifying the transactions itself on the blockchain and seeing how the process goes from end to end.
Cool, thank you. And that's exciting news actually about the testnet. So let me just quickly update the situation. Because of some technical problems, people cannot send messages in the call. So guys, if you have any questions, please send them to Discord. I will, me or Daniel will transfer them to Gidon here. We'll just read them out loud. So yeah, you can start, and actually you can start texting them right now. So I have just one last question for you, and then we'll go through the questions from the public. I was just interested in like about the access control. So a lot of bugs, a lot of critical bugs, they involve hacking access control. Like for example, getting higher privileges that a user should have. So I was just wondering, maybe you can tell us about different access control roles within your protocol.
Yeah, we have quite a few of them. We use the Open Zeppelin access control contract. In particular, the extension version with the default admin roles. So in the hub chain, we have many contracts that has the hub role, which is given to the hub contract. So only the hub contract, which receives all the messages, can call those contracts. We also have like admin and manager roles, which can configure parameters, for example, for like listing new pools or changing the interest rates. These will initially be multi-sig wallets, but it will be later transferred to a DAO to control. And lastly, one thing we didn't have time to talk about during the walkthrough, but we also have a rate limiting mechanism. So we have as well some particular roles there which you can find relating to the capacity and temporarily boosting it and so on.
Cool. Thank you. Thank you for this clarification. So yeah, that's all from our questions. So we can go to the public questions. So the first question we have is, yeah, a person is just asking you to explain the reward mechanism again.
Yeah, so we have 3 rewards we're tracking. So we're tracking for every interest you repay, you get credited with reward points. And then we have 2 other areas, which is that when you, when you deposit or you collateralize a token, you earn interest. But just like that you earn interest, you also alongside that earn rewards. So we have interest indexes to track how much interest you earn, but we also have interest indexes to track how much rewards you earn. Similarly, when you, borrow a token, you're paying interest. So they have interest indexes to track how much interest you owe. But similarly, we have reward interest indexes to track how much reward points you're earning alongside that borrow. The formulas for all of these can be found in the lending formula doc. So I think best to look into the specific implementation through those formulas.
Cool, thank you. I hope this answered the question. And yeah, we are just waiting for. Oh, we have 4 more questions for you. So a person is asking you to explain the spoke guest token. Let me just read out his full question. So when you say some token are not breached, that means the tokens are stored in spoke. If so, in which contract those tokens are stored?
Yeah, that's correct. So spoke gas token and spoke ERC20 token, both of those, for those contracts, the tokens are not bridged. And where they're stored is directly in those contracts itself. So you would have like a spoke gas token for like say Ether or an Ethereum, and that would store all the liquidity in that contract. And then you have, let's say you wanted to add link into your protocol, then we would deploy a spoke ERC20 that would store the liquidity of link. For each token, it would have its own spoke gas token or spoke ERC20 token. So one contract stores the liquidity of one token. Yeah.
Okay, thank you. So the second question was, I posted it in the chat. I'll just read it out because I can't really understand if it's written correctly. So what is an entry point for a user?
Yeah, what is the entry point for a user? I think it's meant to say. So I mentioned like entry points. So what I mean by entry points is just what is the end user address? What function are they calling? So the way you would deposit or the way you interact with the protocol is through the spoke, and then messages in the background are relayed to the hub. So I would say the entry point for the user is the spoke because they're not directly interacting with the hub. The way they communicate with the protocol is through these spoke contracts. So that's what I meant by entry points.
Cool. Thank you. So yeah, another question was like, can we send messages from one spoke chain to another, like from spoke to hub and then again to spoke?
Yes, that's possible. So one of the operations, one of the functions inside Spoke Common is like borrow, for example. So a practical example could be that it's very costly to do an operation on Ethereum because of the gas costs, but you want to borrow Ether. So what you instead do is you submit a transaction from a cheaper chain, let's say it's Base, and you will say, I want to borrow 1 ETH on Ethereum. Now, a message is relayed from Base to the hub saying the user wants to borrow 1 ETH. We validate and check, like, can the user borrow? Do they have enough collateral? And if they do, then a message is sent to Ethereum to actually credit to send you the 1 ETH. So you've managed to borrow on one spoke when you initiated the transfer on a different spoke. And I think that answers the next question as well about providing an example of sending a message. Yeah, so the borrow is an example of that, which I just went through.
Okay, thank you. Thank you for this. Thank you for this presentation, and thank you for actually taking your time and asking answering all the questions from us and from public. I bet this call and this recording will be very useful to the white hats when they will start looking for the bugs. And thank you everybody who also listened to all this presentation. And thank you guys and happy hunting.
Yes, thank you so much, Gidon and Artem, for co-hosting this call and providing such an in-depth walkthrough. Just a reminder that we have an open channel in Discord. So if any other questions have not been answered, please post them here and Folk Finance team will be happy to follow up. So again, don't hesitate to go on our website and check the impacts and the assets for Folk Finance, grab those bounties and find those bugs. Once again, thank you everyone for attending, and thank you, good luck, and see ya. Bye-bye.
Bye-bye, guys.
Thank you.